So welcome to today's webinar. This is one that definitely Jan and I have been looking forward to. It's on 3D analysis in offshore geotechnics, and the presenter is Christian Olsen from Subsea 7. He's a principal engineer at Subsea 7 and does, we know from experience, a lot of interesting analysis and is dealing with a lot of interesting problems. And he'll present some of those today and discuss the ins and outs of those problems. And then, of course, I hope we are going to have a good discussion afterwards with lots of questions. As usual, it works by you guys pressing the Q&A button, which is at the bottom of the window. And you can type your questions in there, and then we will have a Q&A session at the end. So with that, I'll hand over to Christian.
Okay, thank you. Thank you very much. I'm absolutely delighted to be the first external presenter here for this webinar. So thank you very much for inviting me. I'm very pleased today. So I have a presentation here. I'm not as brave as Christian, and I will not do any live demonstration of the analysis since that tends to go wrong. And I'm also Danish as Christian, born around the same time, where we were all called Christian. So a bit unfortunate. The agenda today: introduction, some counteract design for pipeline installation, and towhead design, torsional loaded foundations, and some template design in complex geometry. I will explain these things, as many of you may not know what these things are. So I'll give a good introduction to each of them. As Christian said, then I'm a principal engineer today at Subsea 7. I've briefly worked for Multiconsult, a consulting company in Norway, and otherwise been working for Subsea 7 for some years. Also have been a part-time lecturer at Stavanger University. Yeah. So first of all, Subsea 7. So what is it Subsea 7 do? Subsea 7 basically install infrastructure on the seafloor, mainly for the oil and gas industry, but also the occasionally wind turbine projects. So we install pipelines and structures, which you kind of see on this structure, on this slide here. And we have a series of vessels that do the job. And in the office, we have engineers who do all the design for these structures. And I then work in a small team of geotechnical engineers who do all the foundation design for these structures. And today we'll talk a bit about pipelines, counteracts for pipeline, and towheads and templates. So first of all, counteract design. So this is a case study based on a paper that was published in 2014. And we then reanalyze this today and compare to Optum's Optum G3. And that's the first case here. So when you lay a pipeline, you have some top tension. And if you lay straight, then everything is going fine. But if you lay it in a curve, then there needs to be friction on the seabed. Otherwise, the pipeline will start to slide and just follow the vessel, and that's inconvenient. So if the seabed friction is then insufficient to lay in a curve, then you need to install something. We call those counteracts, and that's what we'll talk about here. This illustration down here shows the pipeline is going along here in a curve, and to make sure we can install in this curve, we put in these counteracts. The case study is from the Storegga slide, which happens about 8,000 years ago in Norway. This illustration over here shows the area. So it's basically the size of Britain, Great Britain. So it has been a massive slide. It can be seen also today in Scotland, and it's believed to have removed the land connection between Denmark and England at the time. So the soil conditions are very much changing. They can be between 1 and 200 kilopascal, basically at the surface. So one kilopascal is extremely soft clay. And we needed to do a counteract design that was applicable to all the locations. And we could allow for large displacements of the counteract, meaning we don't need to worry about the counteract moving 10 centimeters when we load it with the pipeline. And we also had to maximize sea state for installation and recovery. Reason being, it's very expensive in Norway to be waiting on the weather. So these counteracts had to be installed in all weather conditions. So we didn't have to wait for the weather conditions. So this is the counteract. The project has been completed, of course, many years ago. They were cylinders, 6 meters high, 4 meters diameter. And then we put in a inner mechanism to stop it for penetrating. If we were to hit these 1 kilopascal type soils, then they would have just disappeared without this inner mechanism here. And some pictures here from the actually offshore campaign with the counteracts. The original design was completed in Abagus, and also we did some analysis with the software Flac. We used a interface of 0, so we didn't need to consider the dead weight, since once it's penetrated, then the interface is holding up the weight of the counteract, so we didn't include that in the analysis. We worked out the penetration would vary between 1.5 and 4.5 meters, and the seabed is sloping. So we also needed to include that in the analysis, and also the occasional case where one of the counteracts will be tilted installed. So we had many scenarios to be analyzed. In today's presentation, I'll only talk about the one case where we have flat seabed and the counteract has penetrated to 4.5 meters. The horizontal load is applied at the pipeline height, so a bit above the seabed, 0.2 meters. And we have the results on the slide here for the Abagus analysis, and it gives us a displacement of 13 millimeters. 130 millimeters, and the load is 140 kilonewtons. What's notable here is it hasn't gone completely plastic at this time, but it's very close to the limit. So in the Optum G3 analysis, I've made a model. We used the Tresca model with a gradient soil profile. The soil volume, I selected a 25 by 25 by 10. Just to have it large enough, we're using a rigid shell elements and a 24 prism seen over here. And interface of 0.0 so that the self-weight is not included in the analysis. And the load is then applied at sea level, but or at the surface, but I included an upwards and a downwards load pair, so that includes for the moment. In this analysis, we used lower, mixed, and upper bound elements, and we made 3 iterations from 1,000 to 10,000 elements. So the total run times for all 3 is 7 minutes and 22 seconds. So it's rather fast. The results are plotted here in number of elements and load. So you can kind of see the quality of the results. You can see it hasn't quite converted to very narrow, but at the same time, a very narrow distance between the upper and the lower bounds. But you can see that there's a tendency for a load here around maybe 169. So these results are slightly higher than the Abagus, but at the same time, the Abagus model has a very low stiffness and hadn't gone fully plastic. So I think the quality of these results are quite good. And and also the runtime here is only 7 minutes and 22 seconds for all three, both upper, lower, and mixed. We could maybe have gone higher up and analyzed 20,000s as well, just to see if it converts better. So the next topic is towhead design, and I'm sure that very few of you will know what towhead design is. So of course I'll give an introduction to towheads. I will define the problem. I'll show some PLAXIS 3D results, and then provide a comparison to Optum G3 results. So towheads is something that's unique to Subsea 7. It's something we install from the coast of Great Britain, where the idea is that you have all the pipelines required for an oil field is put into what we call a bundle. So the bundle is seen here. So in this one, there'll be several control cables, power cables, oil pipes, gas pipes, water injection, maybe gas injection. There's a cross section seen over here. And the idea is you then put a towhead on either end to connect up in field. With this method, you can then take all the infrastructure more or less out to the field in one go instead of mobilizing several vessels. So this has proven to be very cost efficient on many projects. So the advantage here really is that you have a limited installation time. But you do have some very, very big structures here to design in either end. There's another picture here showing from the beach where you have a tow vessel. So this vessel here is pulling as everything is leaving the shore here. And then there will be another vessel, a tailing vessel in the back, and they'll then drag this out to the field. There's a illustration down here of a towhead in the field where it's then connected up to other seabed infrastructure. Typical for the towheads is that they're subject to trawl loads, and these are often the governing design loads. And the towhead either needs to be installed so it's smooth and the trawl gear flows over and only kind of leaves friction on it. The other alternative is that you can also allow it to actually be hit fully off the trawl gear and then kind of get a bit more stuck, and then the load will increase significantly. So the shape of the towhead is extremely important, or any structure subject to a trawl load. So often it's recommended to complete laboratory tests of these structures. So there's an example here of a fishing net that's hitting a structure. And as you can see, the fishing net is actually quite large, and it will give a very large force on the structure. So if it's a large structure, then we normally would do tests to find out what is the trawl load on this geometry, rather than using the codes, the load given in the code, because the load given in the code is often very conservative for your geometry. So there can be a lot of money to be saved if you get a much more accurate load. So in this case study, I've used a towhead that is shaped like this. This towhead here has tubulars on the edge, so you can imagine that the trawl gear gets stuck a bit underneath here. So if the trawl gear comes flying over here, then the load will be applied on this corner. This load will then lead to a torsion and an overturning at the same time. The size of a typical towhead is 6 meters wide, about 20 meters long, and maybe 4.5 meters high. And the trolley load is then applied, of course, on the underside of the tubular, not on the top, since if it snags underneath, then that's where it's applied. And in this case, the trawl load is 661 kilonewtons at 20 degrees. I've selected a soil strength of 38 degrees for this example. Soil weight of 9.5 kilonewtons per cubic meters. Then also the center of gravity has been shifted a bit away here. The shifting of this makes it less resistance, less able to resist the torsion. So it's quite important to get that factor in as well. There's some other errors on this diagram, but it's this load here that we will focus on during this presentation. So to then design this towhead, the most important thing, of course, is to have the self-weight of the towhead as low as possible. In the present case, we imagine that the towhead weight could be much lower, but it needs to be able to resist the trawl load, and therefore we need to increase the weight. So any weight we apply additional here is money that's spent on Fortinet. So the design objective is really to lower the weight of the towhead to an absolute minimum. And as I said before, the load is applied on this corner here, so it gives both overturning and torsion at the same time. To then find the minimal load, I proposed here there's two load paths to be followed. It's illustrated in a 2D VH diagram, which is a bit maybe incorrect for this application, but it really illustrates it well. So the idea is that we need to have as little self-weight as possible. So first we apply an overweight. This is in load path 1. And secondly, we then apply the actual horizontal load. Then we end up being inside the stability envelope, but our job is to find out how low can the self-weight be. So then step 3 is then to reduce the self-weight until we then hit the stability envelope, and then we have the minimum weight that can be applied. The other option is a bit more guessing, load path 2. Then you guess a dead weight, and then you apply the horizontal load, and you see if it failed or if it didn't fail. So if it didn't fail, you reduce, and you keep guessing until you have the correct dead weight, the lowest possible one. So this load path 2 is more complex. It takes more guesses. So load path 1, of course, is recommended. So typical, we'll design this in PLAXIS 3D. I prefer to use plates in PLAXIS. Others prefer maybe to use solids, but this model here is based on plates. An interface of 1.0 is selected in this case, which is maybe not accurate. Maybe you should have selected a lower interface, but for the present case, we selected 1.0. There's a mesh refinement where you manually have to refine the mesh in PLAXIS around the foundation skirts or in base plate, and so on. And then, of course, on the bottom here, you have a very rough mesh. The challenge in PLAXIS is that you will need some expert knowledge here. There are some talks about what to do about the dilatancy angle in PLAXIS, and also interface strength and so on. I'll not go into that in the presentation here. The dilatancy angle and all that is a bit complex. When you try to analyze something that's both failing in torsion and overturning at the same time, you'll find that load path 1 is very difficult to model in PLAXIS, and therefore instead I've used load path 2. So then you need to come up with a series of guess for the dead weight. So I reduced it from 3,000 down to 2,400 kilonewtons. And we then see the results here. So in PLAXIS 3D, the lowest possible weight that I've come up with is for full yielding here is 2,400 kilonewtons. I tried 2,300, but didn't work. And it's a bit difficult to see it on the illustration here, but this is a combined overturning and sliding torsional loading at the same time. since I weren't able to reduce it to 2,300, I of course should have keep guessing between there to get the optimal solution. But for this example here, I haven't done so. So the Optum G3 model is I used a model space of 100 by 100 and 30 meter deep. It's a much too large volume, but the adaptive mesh optimize it very quickly and find out where to put the elements. In Optums, you need to apply an interface where you want to apply the load. So there's an interface on the top. You can see that here. And the load is then applied on this corner. I think there's a mistake in this figure here because this should have been a red load. No, that's fixed, sorry. Yeah, sorry, that's right, no mind. That's the fixed Trawl load, yes. Then I also built in a, you can call it a mesh help soil volume underneath here, just so this has a greater possibility of getting a refinement in this area. And the Mocolom drained material model is used for the sand in this case. I only just used the mixed element in this case. 4 iterations from 1,000 to 10,000 elements is used. Runtime is 2 minutes and 35 seconds. So this is very, very fast. The result is the dead weight is 2,275 kilonewtons. And the failure mode is more or less identical if you go in and have a look to the PLAXIS 3D results. It's a overturning and torsional sliding. It doesn't really slide since it does push the soil in front. So it's not really sliding as such. It's a shallow bearing failure. But the model is very fast to build, and the runtime is very, very fast. So in Optum G3, the lowest possible weight is very easily found with the load pass 1. I can maybe just explain that I used a weight of this material, and then I had a load I applied upwards to then reduce the load. And yeah, so I started with an overweight and then reduced the weight down to 2,275, I think I wrote in the price slide. So that's roughly 12.5 tons less than the PLAXIS 3D model. I will admit that the PLAXIS 3D, I should have come up with more guesses and keep going until I reach the lowest possible. But it is time consuming, especially compared to the Optums. Just to give you also a picture of what that actually means in money. So 12.5 tons finished, fabricated, being handled. It needs to be placed on the beach and then welded on, dragged out to the field. So total installation cost, all included, it's somewhere between, of course, the price is a bit dependent on welding and so on, but roughly speaking, 150,000 to 400,000 pounds. That's the cost difference for these 12,500 tons. So that's a lot of money for this particular case. Then the last case today is what's called templates, and I'll just introduce it. I'll talk a bit about the case, some load cases, the analysis, and then some discussion on this afterwards. So a template is the structure that combines the well, connects the well to the pipeline, and the pipeline then takes it over to possibly a platform. So the template is where the drilling takes place, and then you connect up your pipelines to the template and get the oil flowing through there. So it's a key infrastructure. It's very important. Typically, these ones are about 250 tons, 15 by 15 meters. And the side load is normally drilling related, or occasionally it could be trawl loads as well. They're installed from vessels. There's an example here. where you see such a template on the back deck here. There's a Subsea 7 vessel here. It may be difficult to appreciate the scale, but this is a large vessel, and the structure is quite large. I think the suction can height on this one is around 8 meters. So it's a very, very large structure. So if these are installed in soft clays, they will have what's called a suction anchor on. And if they're installed in sand, they'll have smaller skirt type structures. So these vessels, they need to have a crane capacity of around 400 tons, and then the day rate for these boats is maybe typically between $150,000 to $250,000 dollars per day, in that range. So it's a lot of money that's used to install these structures. The template design I've used in this case study is 20 by 20. It has a height of 6 meters, and it weighs 2,733 kilonewtons. It has 4 footings, and there are some smaller skirts on these footings. It's a bit difficult to see here. Also, the clay in this case is 55 kilopascals, which is very high typically for North Sea type soils. And there's an interface between the structure and the clay, and this one is modeled as 0.5. In this scenario here, trawl loads have been applied. And in the present case, I've just seen what the difference is if the trawl load is applied on the corner or if it's applied in the middle. In the middle, that would mean that the trawl load is applied all over the structure and then pulls at the same time on the structure. So it's this case here is to assess the difference between having a corner load and a central load. In both cases, they're applied at an angle of 20 degrees, which is quite normal as the vessel will be pulling upwards with the trawl gear. And I've modeled it as a rigid volume here, and then skirts in the soil. And to analyze this, I've used the Tresca material. I've used mixed upper and lower elements, 3 iterations, starting off with 1,000, 2,000 in 1 or 2 of the models, up to 20,000 elements. And there are 2 cases here, and a total of 6 runs at a runtime of 21 minutes and 34 seconds. So of course, this is a lot more time consuming when you go up to 20,000 elements, but it is seen here in the number of element and load diagram that it doesn't convert at 5,000. You need to come down to or come up to about 20,000 elements before the tree bounds starts to give you a similar value. So the result here is that if the load is located in the center, you will have 5,914 kilonewtons. And if it's on the corner, the capacity is 4,706 kilonewtons. So having a torsion on this foundation really brings the capacity down. Of course, this is these capacities here are far higher than the actual trawl load. So the trawl load is not governing in this case for the structure. Also note that for less than 2,000 elements, we actually see that the upper and lower bound values have been switched. It's not uncommon that this happens in Optums for very rough meshes where it's very complex geometry. That's why you then need to do the sensitivity of the mesh to come up and investigate when it becomes more smaller distance between the upper bound and the lower bound, and then see how the mix is coming in between here. So some discussion. So this problem here is really highly complex. The 4 individual footings are loaded completely differently, and the load has to be distributed between these ones. Of course, it's so complex that the first iteration there's some discrepancy between what you would expect with upper and lower bound. But it was really easy to build a model. The runtime does increase when you go up to 20,000 elements for 6 runs instead of just having 10,000 elements, so 20 minutes thereabouts. However, you do get a good, I think, sense of the capacity when you have the lower bound and the upper bound and then the mixed element as well. So it enables you to quantify the quality of the results. And just last year, then the Trawl load is never this high. So this particular template is it's not a concern for the Trawl load in that case. And I think that was me. Maybe a bit fast. I can't see the time here.
Thanks a lot, Christian. No, that was absolutely perfect. That was really interesting. Thanks for that. And we will take some questions now. There are some in already that I can try to go through. I have some myself as well, but let's take the ones of the participants first. There's one on the type of interfaces you used in Abagus. So I think you mentioned this was 2004. That
14.
was done. 14. Okay. So is that something you can say anything about the modeling of interfaces, maybe Abagus versus
unfortunately, at the time I didn't do the analysis, so I don't remember this detail. The paper was published in 14, and I think the work was done in 11. So it's a few years ago. So unfortunately, I can't say it about that.
Sure. But I think it's fair to make the general comment that interfaces obviously are very important, and that it is more or less convenient to define them. And being an Optum man, I know that this is something we've paid a lot of attention to, and I think it works really quite well. So of course, having a strength reduction of strength at the interface is something that you often do, and also when it comes to undrained analysis, a tension cutoff is something that is often essential, and that's really quite straightforward to do.
I think you showed that in one of your previous presentations. I think on the monopile for wind turbines. I think you showed that.
That's one case where if you don't have the tension cutoff, it really doesn't make much sense. The results the soil sticks to the pile on the active side. So good. Then there is a question: why did you see such a big difference between PLAXIS and Optum? And I think you kind of touched on that.
It's possible that the PLAXIS model could come down to say 2,301 kilonewton, but it requires a lot of work to follow the other load path. What I've experienced is that if I need to reduce the load of a structure in PLAXIS while it's subject to torsion, then sometimes it becomes a bit unstable. And maybe it's my lack of experience working with this problem, but load path 1 has always been a difficult for me to do. So maybe if you were to go for load path 1 and you had more experience than I, then you could make it work quicker. But I've chosen to use load path 2.
Sure. But I think that also illustrates a more fundamental point, that this simulation approach to things as opposed to limit analysis is kind of problematic. Maybe problematic. Quite often you get away with it, right? But limit analysis answers the question of about what magnitude can I increase my loads, my multiply loads, and then you have some fixed loads as well. So there's no simulation in a limit analysis, whereas if your only sort of tool in the toolbox is a load displacement analysis, you have to make some decisions that are not always straightforward to make.
Yeah.
So I would say, also speaking with my Optum hat on, that one of the differences between PLAXIS and Optum in 3D is the elements used. So you mentioned the three elements, the upper and lower and the mixed element, and the mixed element in particular is a very accurate element. It turns out, I mean, based on experience and sort of verification comparison to existing solutions, whereas the element used in PLAXIS, I believe, is a standard 10-node tetrahedron, which is not as accurate. So there might be something in that as well. I don't know. That's actually covered in the one of the videos, Introduction to Optum G3, that's on our YouTube channel, if any of you are interested in that little detail, which of course is a very important detail. So is there any comparisons between PLAXIS and Optum for the soft clay? I guess that was the first application, the counter.
No, that was never, that particular design was never completed in PLAXIS. It was only done in Abagus and Flac at the time.
Okay, yeah. And just on that, on that question of different programs, do you internally in the company compare the results of different programs? Is that something you make a habit of, or is it if one program gives something that looks reasonable, then you accept that? Or
if it's a very expensive piece of infrastructure we'll design, then we'll probably look at the same problem in more different ways, or maybe just do a hand calculation to validate that it should be logic. But a torsional loaded towhead, as you see here, it's difficult to solve that by hand.
Sure. And there's a question that I'd actually like to answer myself. Can we choose the load path in Optum? And the answer to that question is yes and no. If you do an elastoplastic analysis, so an actual simulation of what happens, so then you have some sort of load path, you have the order in which the loads are applied. So in that case, the concept of a load path makes sense. But if we are talking limit analysis, then we are dealing with the ultimate, with just determining the ultimate limit state, and not with how we get to that ultimate limit state. And that's very often a much more convenient way of looking at things than having to go through a simulation to get to the ultimate limit state. I think it's something that's a very natural and sort of essential in many ways part of how civil engineering is approached. If you think slope stability, for example, you want the factor of safety. How do you get to failure of a slope? Well, that's not really the question you're asking. You're asking for the factor of safety. So whereas if you only have load displacement analysis at your disposal, you will have to somehow come up with a fictitious simulation to get to the ultimate limit state. Sometimes that's straightforward. In other cases, it's less than straightforward. And in those cases, limit analysis really is I believe, a powerful tool. And a related question in PLAXIS and in Abagus, I guess, as well, when you use load displacement analysis, you get load displacement curves.
Could you repeat that?
Yeah, I mean, there's a couple of related questions on when you use PLAXIS, and the same with Abagus, when you use elastoplastic analysis, there is the need to somehow select some elastic parameters.
Yeah.
Whereas with limit analysis, it's only the strength parameters that are in play.
Yeah,
And
exactly. You could say in the particularly in the case with the turn point, the counteracts, the displacements are really, they don't matter. If this has displaced 20 centimeters, then it would still have worked just fine. It's really the capacity that we're looking for in this case.
sure, yeah. So you're saying the elastic parameters are not that important. You just pick something that is kind of a reasonable ballpark figure when you do your elastoplastic analysis.
Yeah. It of course needs to be as representative as possible. It also depends on what you're doing. But if you're doing a ULS design, then it does not matter really how much it moves. That's
Yeah. So then in
that's
that
the
case,
basis.
sure. Then in that case, the elastic parameters are kind of like almost like an algorithmic parameter that you choose to get things to run properly.
Yeah.
Which of course that decision is not necessary to even consider when using limit analysis. So I think that's a good thing as well. So did you do any? Did you look at? There's been quite a lot of interest in torsion recently. So I think torsion is one of the cases that's not considered by the codes at all, really. If I'm not mistaken, it's definitely not part of the.
There's a very simple expression based on a lower bound presented in DNV GL. Okay. Which is very conservative. So if you choose to do a hand calculation for torsion loaded towheads and you follow the lower bound equation in the code, you'll end up with a very heavy towhead and it'll be extremely expensive. So one of the codes does have a torsional loaded equation mentioned that you can use.
Okay, interesting. Let's see what else we have. Then maybe I would like to ask a question myself. The towhead application was a really interesting one, Christian, and you showed by doing some, let's say, more careful calculations, you could actually there was some large pound amounts to be saved. And what about the friction angle that you use in those cases? How do you pick that? We had a webinar some weeks ago that you might have caught about the difference. We talked about it as well. The difference between the plane strain and the triaxial angles.
In the present case, then the friction angle of 38 degrees, that is very high for offshore sands. So that one is not applied any material factors as such. But in this present case, then it's just a triaxial test based on possibly just based on CPT. So it's this was a case study. It's one that's picked based on a previous project, but it's not. Some of the values have been changed a bit.
Sure. Okay.
But you would normally use the triaxial test. DNV normally prefers to use the triaxial test, whereas ISO has actually swapped recently over towards wanting you to use the plane angle, at least in the bearing capacity formulations.
Okay. Yeah, you can make both cases, I think, when it comes to the bearing capacity equation, right?
Yeah.
But the question is when you then do 3D calculations, and the point with this webinar we had the other day was we have a new model called the FAST, FASD, friction angles, stress state dependent, where you actually enter both the plane and the triaxial angles, and you then have basically a modified sort of failure envelope that tends to match experiments fairly well.
Yeah.
So with a significantly lower friction angle in triaxial compression than for plane strain and also extension. So that might be something that could be of interest. Then there's a question of whether you have done any Optum modeling for structures founded on rock berms. And I know that's something we've discussed as well, maybe not in an Optum context, but it's something you deal with. And I saw a rock berm also in your very nice figure there of the underworld.
Yeah, we have also done that on a recent project where you have a soft clay and then a rock berm on the top there. So we have also used Optums for that. I didn't go into high details with comparing to PLAXIS, but they looked very similar. Yeah.
Okay. Yeah. So I guess the main challenge with rock berms is very high friction angles.
The main challenge actually, if we're just talking PLAXIS right now, is if you have a soft clay and you put rock on the top, then what stiffness to pick for the rock? If you pick a high stiffness for the rock, then you get into some numerical stability problems because you have something that's stiff on top of something that's soft. Then you can be in some problems.
Yeah. Okay, interesting.
There's one asking here, any penetration records in actual from PLAXIS, Optum, or Abagus? I'm not sure if what is meant here, but the penetration is not analyzed. These structures being installed, how deep they come down, that's not analyzed in these softwares. But we record whenever we install something, or mostly we record how deep it penetrates, and then of course compare to our analysis, so we can get better in doing these assessments.
Yeah. Real life tests, is that something that is available? I guess they are very, very difficult to come by, but I think it's a valid question when you do these analysis, whether it's 2D or 3D, but how do you actually, at the end of the day, validate them? And of course, the best case you can come up with is to actually have full-scale tests. Is that something that at all is something that you are aware of? That I mean, for monopiles, of course, there's these, I'm not so sure it's full scale, but definitely large scale tests that are really quite useful as a means of benchmarking your numerical analysis.
I know of very limited full scale offshore tests. You can say whenever we recover a structure from the seabed, and that's partly a full scale test, and that does compare to models.
Yeah. So there are more questions about stiffness parameters, and just to emphasize again that all the analysis we saw here were limit analysis, where only the strength parameters are relevant. So in some programs, depending on what type of analysis you run, you have to pick you have to pick some elastic parameters if you're doing an elastoplastic analysis. If you're doing a limit analysis, there are no elastic parameters to be considered at all. So that's like kind of let's say a convenience, and of course they're not relevant to the failure loads. But our serviceability, so let's say deformation analysis, do you have applications where that's relevant, Christian, where you look at actual deformations and they mustn't exceed a certain threshold and so on, like more along the lines of what's done in typical onshore applications?
Yeah, and if we maybe not take the towhead as an example, but other times we may land a different structure on the seabed, and we found out that this structure will move. It has to be protected from other structures, so we need to put a cover on the top. You imagine the structure is connected to maybe pipelines coming in from 2 directions, maybe 4 directions, and these pipelines are so massive with hot flow through them that the temperature in the pipes will simply just move the structure. We are then trying to find out how much it's going to move, to then see if it's going to hit the cover. Because if it also hit the cover, then the whole thing is going to move. It's a bit like a bridge. in the nice heat at summer, it's going to expand. Sure. And you can't stop it. So you need to find out how much structure occasionally moves to then see if it's going to hit a cover. We have done that on some projects. So then, of course, the elastic properties are quite important.
But those movements, I guess, would be what would typically be classified as large deformations. So with the soil actually being at failure.
Yeah.
So that's some really challenging problems, of course.
That's for a different session, maybe. That's
yeah.
Yeah, that's maybe.
Let's keep that for the future. Great. I think that was it. And
there's just one question here. There's for PLAXIS compared to options, did you complete any analysis for pure torsional capacity for drained soils? Someone talking about the Finney and Morgan paper. I didn't compare actually to the Finney and Morgan in this study here, but the Towhead case is actually for more or less pure torsional loaded capacity, and I believe that the results coming out are as accurate as they can be.
Yeah. This, I think, refers to this question that we've recently done a bit of work on torsional capacity of foundations for the drain case. So the Finney and Morgan equation, or the solution there, which I believe is actually an exact solution, is for the undrained case.
Yeah.
You can adapt that to if you have nothing else, you can adapt that to the drain case and substitute the friction, the undrained shear strength with some sort of the normal stress times the tans of the friction angle.
Yeah.
And you get something then, but it turns out that that's actually rather conservative. And so we've come up with actually an analytical solution for the drain case recently. I can send that to you. That might be useful. I don't know, but it seems to compare well with what we get numerically. And
okay.
It has about the capacity is about twice what you have with this Finney and Morgan adaptation. So
okay, that's huge.
Yeah,
that's a lot of money.
Okay. Okay, Christian. So thanks again for a very interesting presentation. It was really inspiring to see these types of problems being solved, and where it's important really to have accurate solutions, and where the accuracy of your solutions and the quality, you could say, of your engineering really has a direct and tangible outcome in terms of the numbers, the money numbers. So that was really interesting to see, and thanks for that. And thanks for the participants. And we will have another webinar in a couple of weeks, which should also be very interesting, and details about that will be sent out. So thanks for today.
Yeah, thank you very much. Thanks. It was a great pleasure to be the first external presenter here. So thank you very much, and thanks for the good questions also.
Yeah, great. See you.